So this lecture will be on linear spaces. So this is very elementary, but all these lectures will be based on these definitions. So we will be talking about linear spaces. So a definition: X is a linear space over a field which will be represented by K. So this field will be either the real or the complex. If X is a set with two operations, an addition and a multiplication by scalars. So I'm assuming that there are two operations. The addition will be an operation on X, which will satisfy three conditions. So if X and Y are elements of X, I will define a new element of X represented by X plus Y. And this operation plus satisfies three properties, as I said. The first one is that it's commutative, which means that X plus Y is equal to Y plus X. And it's also associative, in the sense that if you take X plus Y plus Z, which means that you consider 3 points in X, Y, and Z. You first add Y to Z, and then you take this new element and you add it to X. This is the same thing as adding first X and Y, and then add the result to Z. And finally, we will assume that this set is a group, and we will represent its neutral element by 0. So this means that there exists an element 0 in X, such that 0 plus X is equal to X. This holds for all X. And we will represent the inverse element of X by minus X, which means that minus X plus X will be equal to 0. So minus X will be the inverse element to X with respect to this addition. So now there is a second operation, which is the multiplication by scalars. So in this lecture, I will represent by alpha and beta the scalars. And this multiplication will satisfy two properties. The first one is that the multiplication is associative. This means that if I take alpha times beta, which is now a new element of the field, and I multiply that by an element of X, well, this will be equal to alpha times beta X. And of course, this holds, I'm assuming this for all alpha and beta in the field K, and for all X in X. And it's also distributive. And this means that if I consider alpha plus beta times X, this is equal to alpha times X plus beta times X. Or if I take alpha and X plus Y, so alpha times the element X plus Y, this is also equal to alpha times X plus alpha times Y. And I will almost always forget about this point. I'm just representing the product of a scalar with an element of X just by writing both letters. And also, we will be representing by 1 the neutral element of the field k, which means that 1 times x will be x, and for all x. So these are the properties of the multiplication by scalars. Okay, so two very simple properties before we go on. First, I claim that if you take the element 0 in your field k and you multiply 0 by x, you get the element 0 in your set x. And why this is so? Well, because if you take 0, well, this is, of course, I can write it 0 plus 0, and I consider that time x. What I get? Well, on the one hand, this is 0 times x. On the other hand, by distributing, this is 0 times x plus 0 times x. And therefore, now if I subtract this element on both sides, what I get is that 0, it's indeed equal to 0 times x, right? So this identity just, I'm using the same notation for two different objects. This is the neutral element in x, while this one, it's the neutral element in k. And what I'm saying is that for any x in x, if I take 0 times x, I get the neutral element. So this is one property. And the second property is that, remember, if I have an element x, I'm representing by minus x the inverse of x with respect to the addition. And what I claim now is if you take minus 1 and you multiply that by x, what you get is that this is minus x. Right? So this is minus 1. It's an element of the field. I'm multiplying minus 1 by an element x of the set x. And what I'm saying is that this is the inverse of the point x. Well, and how you prove that? Well, you know that 0, as I just proved, this is equal to 0 times x. Well, but I can write 0 as 1 minus 1 times x. Now I can distribute that. So this is 1 times x plus minus 1 times x. This is the neutral element, so this is x plus minus 1 times x. This is equal to 0. So if now I sum the inverse element to x in both sides, so I get minus x equal to minus x plus minus 1 times x, right? So this follows from this identity. I'm just summing on both sides the negative element of x. Well, these cancel because this is the inverse element to x. And what I get, it's what I claimed, is that, it's what I claimed here, it's that minus x, it's indeed equal to minus 1 times x. So let me give you now some examples. Well, one, let's take x to be the set of all polynomials. So Pt, it's a polynomial for t in R. And we will take k as the real set. So, of course, we can define additions of polynomial in the usual way and multiply a polynomial by a real number and get another polynomial. You can check that indeed x with the usual sum and multiplying a polynomial by a real satisfies all the assumptions I presented in the definition. Of course, you can extend this example to the case in which you consider polynomials in n variables, t1, tn, and this is also an example of a linear space. Another example which will appear often in these lectures are the space of continuous functions. So you take a subspace, or let's say a space Rn, you consider C of Rn the space of continuous functions, and either you take them as taking a complex value or real values, and in both cases, well, C, your field will be either the complex plane or the set of real numbers. So you can also check that this forms a linear space, as you can add continuous functions to get a new continuous function, or multiply a continuous function by a real or complex number, getting a new continuous function. A third example, which also will appear quite often, is the space of sequences. So you take X to be the space of sequence Aj for j larger than 1. So this is a sequence A1, A2, A3, and so on, in which Aj either take value on C or on R. And again, if it takes value on R, you take the field to be R, and you can multiply a sequence by a real number by multiplying each entry by that real number, and you can also add sequences. So it's clear that X defined as the space of sequences forms a linear space. Another example is where you take an abstract space, omega, with a sigma field F and a certain measure mu defined on this sigma field. And now you consider the space X to be the space LP, which is the space of all functions from omega, say, to R, such that which are measurable with respect to the sigma field F, and for which the integral over your space omega of F to the power P d mu, it's finite. And of course, now you take K to be the space of real numbers, and again, you can check that, well, it's known that LP, it's a linear space. It's easy to show it, and therefore this is another example of a linear space which will appear also in these lectures. So from now on, I have a linear space X defined over a field K. And what I want to discuss now are sublinear spaces. So if I have a set Y, which is a subset of X, I will say that it's a sublinear space if given 2 points X, Y in Y, and given a scalar alpha in K, then alpha X plus Y belongs to Y. So this is the definition of a sublinear space. So again, let me insist that from now on in this lecture, I have a fixed linear space X defined over a scalar field, field K. And this is a definition. So given a subset Y of X, I'm saying that Y is a sublinear space of X if for all y, alpha in K, all X and Y in Y, alpha X plus Y belongs to Y. And let me give you some properties or some examples. So the first one, it's very easy. If you take Y to be the set of the element 0, this is, of course, a sublinear space well, because if you multiply 0, we've seen that if you multiply 0 by any number, you get 0. And if you add 0 to 0, it's also equal to 0. Therefore, that y equal to 0, it's a sublinear space. Let us consider slightly more complicated one. Let's assume that y1 and y2 are sublinear space. What I claim is that the set y1 plus y2, it's a sublinear space. And how do I define y1 plus y2 if I have two sets? Well, y1 plus y2 will be the set of all x plus y, such that x belongs to y1 and y belongs to y2. So this is a definition. Whatever subset y1 and y2 of x, y1 plus y2 will represent the set of all elements which can be written as the sum of an element of y1 with an element of y2. And now what I'm claiming is that if y1 and y2 are sublinear spaces, then the sum, it's also a sublinear space. And to prove this claim, what I have to check is that this condition holds. So let me take x in y1 plus y2, y also in y1 plus y2, and a scalar alpha. And what I have to prove is that alpha x plus y belongs to y1 plus y2. So what I want to prove is that this element is an element of y1 plus y2. Well, since x is an element of y1 plus y2, this means that x it's equal, by definition, to x1 plus x2, where x1 belongs to y1 and x2 belongs to y2. In the same way, if y is an element of y1 plus y2, this means that y it's equal to y1 plus y2, where y1 belongs to y1 and y2 belongs to y2. Now, since y1 it's an linear subspace, let me write it over here, I'm sorry. So since I know that y1 it's a sublinear space, what I know is that alpha x1 plus y1 belongs to y1. And I also know, because y2 it's a sublinear space, and as x2 and y2 belongs to y2, that alpha x2 plus y2 belongs to y2. But this means that alpha x1 plus y1 plus alpha x2 plus y2 belongs to y1 plus y2 by definition of y1 plus y2, right? y1 plus y2 are all elements which can be written as an element of y1 plus an element of y2, which is the case. So I know that this element belongs to y1 plus y2, but I can, by using the properties of the additions and multiplication by scalars, rewrite this element as alpha x1 plus x2 plus y1 plus y2. And, well, what is x? X is x1 plus x2, so this is x. And y it's y1 plus y2, so this is y. And therefore, we proved that alpha x plus y belongs to y1 plus y2, which is exactly what we wanted to prove. So we just have shown that if we have two linear subspace, then the sum of these two spaces is also a linear subspace. Now, a third property is that assume that you have a family y indexed by some set I. Assume that you have a family of linear subspace. So I'm assuming that y theta, it's a linear subspace of X. And what I claim is that the intersection of y theta, let me represent this intersection by y, it's also a linear subspace. So mind that I'm not assuming that I it's countable. I'm just taking any set I, and what I'm saying is that if each set it's a sublinear space, then the intersection it's also a sublinear space. And to prove that the intersection it's a sublinear space, what we need to show is that if we take X in Y and Y in Y and alpha an element of our field K, we have to show that alpha X plus Y it's an element of Y. Well, and this is very easy because take fixed so X and Y, consider theta. Since X and Y belongs to Y, this means that X and Y belongs to Y theta because Y is the intersection, so each element belongs to all sets YT. Since YT it's a sublinear space, this means that alpha X plus Y belongs to Y theta because Y theta it's a sublinear space. And since this holds for all theta, I can conclude that alpha X plus Y belongs to the intersection of theta over I of Y theta. And this is exactly Y. So we proved that alpha X plus Y belongs to Y as we wanted. So this proves that the intersection of linear subspace, any intersection of linear subspace, is a linear subspace. So I will say that a family Y theta is totally ordered if you take any theta 1 and theta 2 in your set of indices I, then either y theta 1 is contained in y theta 2 or y theta 2 it's contained in y theta 1. Right, so it will be totally ordered if you take any two sets in your index set, and either one is contained on the other, or the other is contained on the first. And the fourth property of linear subspace says the following. Well, assume that you have a family which is totally ordered, then define Y as the union of Y theta. Assume that these spaces are linear subspace of X for all theta in I. So I'm assuming that Y theta are linear subspaces and that this family is totally ordered. And what I claim is that then the union of this family is a linear subspace. And again, to prove that it's a linear subspace, I have to consider X and Y in Y, capital Y, alpha in K, and have to prove that alpha X plus Y belongs to Y. Well, since X and Y belongs to Y, this means that they belong, each one belongs to one set. So there exist theta 1 and theta 2, such that X belongs to Y theta 1, and Y belongs to Y theta 2, because X and Y belong to the union. But now, since the family is totally ordered, either y theta 1 is contained in y theta 2 or the opposite. So let's assume without loss of generality that y theta 1 is contained in y theta 2. Well, this means that since x belongs to y theta 1, it also belongs to y theta 2. So we deduce that both x and y belong to the larger one, which is y theta 2. And since y theta 2 is a linear subspace, this means that alpha x plus y belongs to y theta 2. And since they belong to theta 2, y theta 2, they belong to y because y theta 2 is contained in y. And therefore, we proved that y alpha x plus y belongs to y as we needed in order to prove that this union is a linear subspace. So now I want to discuss linear spans. So let me consider a set S which is contained in X. Note that I'm not assuming S to be a linear space, a linear subspace of X. And I want to define the linear span of S. So this will be represented by LS, linear span of the set S. And this, well, by definition, will be the intersection of all sets y theta such that y theta is a linear space which contains S. So I'm taking here the family of all linear subspaces which contain S, and I'm taking the intersection of these linear subspaces. Note that this intersection is not empty because X is certainly a linear space which contains S. So at least X belongs to this intersection. And this is the definition of the linear span. We have just seen that if I take an intersection of linear subspace, I get a linear subspace. So indeed, LS of S, the linear span of S, it's a linear subspace of X. What I claim is that the linear span of S is the smallest linear subspace which contains S. Right, so this is the definition. Now I claim that the linear span of the set S is actually the smallest linear subspace of X which contains S. Well, why this is true? Well, on the one hand, we have seen that LS of S is a linear subspace. Right? Because we know that the intersection of linear subspaces is a linear subspace. So LS of S, it's a linear subspace. Now, assume that we have Y, which is a linear subspace, and assume that Y contains S. Well, but then this means, by definition, that Y is one of these elements which appears in this intersection, and therefore Y contains the intersection, and the intersection is exactly the linear span of S, which means that the linear span of S is contained in Y, and therefore, indeed, any linear space Y which contains S has to contain the linear span, so the linear span is the smallest linear subspace which contains S. Now, a second property of linear spans is the following. Well, if I have elements x1, xn in a space Y, and alpha 1, alpha n elements of the field K, I'll say that alpha j, the sum alpha j xj from j from 1 to n, it's a linear combination of elements of Y. So when I say that I consider a linear combination of elements of a set Y, what I mean is this, that these elements can be formed as finite sums of the multiplication by a scalar of elements in Y. And my second claim about linear spans is that the linear span of a set S is formed by all linear combinations of elements of Y, of S. So what I claim is that this linear subspace is actually equal to the linear combinations alpha j xj, where alpha j's are elements of the field K, xj elements of S, and I'm taking all possible finite sums. So I want to prove this identity. Well, what I need to show is that the right-hand side, and let me call the right-hand side Z. Well, what I have to show is that Z is a linear subspace of X, and that Z contains X, right? In order to prove this identity, I have to prove that Z is the smallest linear subspace which contains S. So I have to show that Z it's a subspace, linear subspace. Then I have to show that Z contains S. And if I show that Z is a linear subspace which contains S, this will imply that Z contains the linear subspace of S, because this one is the smallest one. And then I have to show that if Y is a linear subspace which contains S, then Y contains Z. Because this second property shows that Z is actually the smallest one. So by proving these three facts, I will have the identity between Z and the linear span. So let's prove these three properties here. So first, I want to show that Z is a linear subspace. So to prove that Z it's a linear subspace, I have to take two elements, so say Z1 and Z2 in Z and alpha in K, and show that alpha Z1 plus Z2 belongs to K. But that's very easy because, well, if Z1 and Z2 belongs to Z, this means that Z1 is equal to the sum from 1 up to N1 of, let's say, alpha j xj, where alpha j it's an element of the field and xj an element of S. In the same way, Z2 being an element of Z, it can be written as a sum from 1 up to N2 of beta j yj, where beta j are elements of the field and yj is elements of S. And now alpha Z1 plus Z2 is equal, well, I'm multiplying z1 by alpha and adding z2. So that will be equal to a sum from 1 to n1 of alpha j xj plus a sum from 2 to n2, from 1, sorry, to n2 of beta j yj. And this has this form. Right now we are summing over n1 plus n2 elements. This is a scalar which is multiplying an element of S. This is a scalar which is multiplying an element of S. So it has indeed this form. So alpha z1 plus z2 belongs indeed to the set Z, which shows that Z it's indeed a linear subspace. Okay, note that there was a mistake here. I wrote K when I meant Z. So this first argument shows that Z is a linear subspace. Now I want to show that Z contains S. Well, but this is clear that Z contains S. Take any element of S. Any element of S can be written as, you take n equal to 1, take X, an element of S. X can be written as 1 times X. So it's clear that Z contains S. And therefore, from these two facts, the fact that Z contains S and it's a linear subspace, we know that Z contains the linear span of S, because the linear span is the smallest linear subspace which contains S. Now I want to show the other inclusion, so I want to show that Z is included in the linear span, and to show that Z is included in the linear span, what I have to show is that if Y is a linear subspace which contains S, then Y contains Z. So let's prove that. That's also very easy. So let's consider Y a linear subspace which contains S. And I have to show that Y contains Z. Well, take an element Z in Z. So Z can be written by definition of the space Z as a sum j from 1 to n of alpha j xj, where xj it's an element of S and alpha j an element of k. Well, this is an element of S, so it's an element of Y, because Y contains S. So multiplying an element of Y by a scalar, it's still an element of Y, because Y is a linear subspace. And summing elements of Y gives an element of Y, because Y is a linear subspace. So this is an element of Y. So we just proved that if Y is a linear subspace which contains S, then it has to contain Z, because any element of Z is an element of Y. And so from these three properties, we conclude that indeed Z is equal to the linear span of S. And this is a very nice property because it gives an explicit formula, for each element of the linear spans. Right? You take S, any set, you consider the linear span, which is in principle a very abstract object because, well, by definition it's the smallest linear subspace which contains S. And what we just proved is that we have an extremely simple formula for the elements of this linear span. All elements of the linear span can be written as a finite linear combination of elements of S. And this property will be used many, many times.